to continue our discussion of critical points and intervals of increasing and decreasing and relative maximums and minimums, but this time we're going to look at an example that is not a polynomial. So let's consider the function y equals x squared minus or times the square root of 5 minus x, and let's start by taking a derivative. Well, because this is a product, we're going to need to use our product rule. So the derivative would be, let's keep the first term, times the derivative of the second, which would be 1/2, 5 minus x to the negative 1/2, times -1 for our chain rule, plus, now this time we'll keep our second term, 5 minus x to the 1/2, times the derivative of x squared, which is 2x. So I'm going to go ahead and rewrite that so that I'm in radical form and get rid of these fractional exponents. So when I do that, all of this first term is going to become negative x squared, there's your x squared and there's your negative, over 2 square root of 5 minus x. Then my second term is just going to be 2x square root of 5 minus x. But I'm going to go ahead and put this over 1 so that they're both fractions. Then I want to combine those two fractions into 1. So I'm going to get a common denominator, and I'm going to multiply the second fraction by 2 square root of 5 minus x in both the numerator and the denominator. So when I do that, I get my derivative to be negative x squared over 2 square root of 5 minus x plus 4x times 5 minus x over 2 square root of 5 minus x. But then we could go ahead and use distributive property. So let's change colors here real quick. On this part and get 20x minus 4x squared. And then by combining like terms on the numerator, we now get negative 5x squared plus 20x over 2 square root of 5 minus x. That's the problem that I want to work with when I'm looking for my increasing and decreasing and my maximums and minimums. So let's take this problem and get our critical points. Now, because this is not a polynomial and it is a rational function, what I'm going to do is I want to know what would make this equal 0 or undefined. Well, a fraction is 0 if the top is, or the numerator is equal to 0. So we'll take 5x squared plus 20x and set it equal to 0. And it's undefined when the denominator is equal to 0. So we'll set the denominator equal to 0. And now let's solve those. So I'm going to solve this first part by factoring out a negative 5x. And if I do that, I'm going to get x minus 4. But then I set each part equal to 0. And I get x is 0 and x is 4. Now, on the second problem, or second part of the problem, I'm going to divide both sides by 2. Then I'm going to square both sides and get 5 minus x equals 0. I could add an x to both sides and get that 5 equals x. So there's going to be my critical points. So I'm going to go ahead and make my sign chart using 0, 4, and 5. So remember, to find my, we'll label that y prime, to find my signs for my sign chart, I take values on these different intervals that I have marked here, and I'm going to substitute them into my derivative and see what happens. So let's pick -1 and substitute back into my derivative. Now I'm actually going to take a minute before I do that, and I'm going to go ahead and factor this as -5x x minus 4 over 2 square root of 5 minus x. So if I'm very careful and observant, I'll notice that no matter what value I substitute in to my denominator, that is always going to be a positive. So I really don't have to worry about what's happening in the bottom because I know that that's going to end up being positive. Because when I do the square root of this, because we don't have the positive or negative square root, I want just the primary principal root of the positive value. So then looking at the numerator, if I substitute in -1, I get -5 times -1. Well, that's positive. And -1 minus 4 is negative. So I have a positive times a negative, which will be negative. Pick something between 0 and 4. So I'm going to pick 1. If I put 1 in, I get -5 times 1, that's negative. And 1 minus 4, that's negative. And a negative times a negative is a positive. Pick a number between 4 and 5. Well, I'm going to use 4.5. So if I put that in, -5 times 4.5, that's negative. 4.5 minus 4, that's positive. So I have a negative times a positive, which is negative. And then if I try to substitute in a number bigger than 5, we actually are going to get into trouble with our denominator because the square root of 5 minus something bigger than 5 would be imaginary. So our last value we're going to be able to use would be 5. Now remember when I looked at this with the polynomial, I could sketch in the increasing and decreasing and that would give me an idea of the graph. That is not going to help you with problems that aren't necessarily functions that are not polynomials. So if I were to sketch the increasing, decreasing, that may or may not be what my function looks like. So I'm not going to do that for this one. And I'm just going to look at this and see that this is decreasing, then it's increasing, and then it's decreasing. So we now know when we're increasing and decreasing. So we are increasing from 0 to 4. We are decreasing in two different places from -infinity to 0 and then from 4 to 5. Now the last thing we need to do is determine our relative maxes and mins. So if I look at the problem, we switched from a negative derivative to a positive derivative, or from a decreasing function to an increasing function, which means we had a relative min at 0. So if I go back and substitute into my original equation, now remember the original equation was y equals x squared times the square root of 5 minus x. That was my original f of x function. So now if I put 0 into that, I'm going to get 0. So my relative min is 0, 0. And then at 4, we changed from an increasing function to a decreasing function. So we had a relative max there. And I want to put 4 back into the original problem, not into the derivative, because that will give me 0. But if I go back and put 4 into the original problem, I'm going to get 16 times 1, which will be just 16. And so you have a relative min at 0, 0, and a relative max at 416. Notice it's the same work that we did before. We just have to, in this case, consider that the derivative could have been undefined. And a lot of times in these problems, your derivatives get a little more complicated and you may have to do a little more algebra to find your critical points.